us that f squared is equal to d sub I minus f times d sub O minus f. And so that's kind of a new version of the lens, an alternative version of the lens equation. It is the same as this if you rework this, but sometimes this can be more convenient. And so one place where it is.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, so for lecture 20, we're going to talk about total internal reflection. And so this is an interesting aspect of refraction. So in the previous examples, we've always considered going from some material N1 to N2, which is greater than N1, meaning the speed of light is slower in this material, right? And we've come in with an angle of incidence, theta I, and we've had refraction inside the material, and so I'll call this theta R for refraction. And so the refraction is taking place in a higher index material, which means light is traveling slower in this material. And the result with the general idea that you see is that when light refracts in a higher index material, the ray will bend towards the normal. So if I make this an even higher index of refraction, it'll bend more towards the normal. And in your homework, I think you saw some examples of that. When you look at how much it bent upon refracting into glass and then also in diamond, right? It refracts much more in diamond than it does in glass because diamond has a much larger index of refraction. Whereas, of course, if N2 was equal to N1, there would be no refraction at all. The angle of incidence would be the same as the angle of refraction, so there would be no bending towards the normal. But what happens if we're the other way around? What happens if we're inside of a material, right? And I'll draw the normal to the surface of the material here. And this time I've got a ray that's coming from the higher index material. Right, so this could be glass, for example, and this could be air. So we've somehow transmitted some light through the glass or from the glass, and it's going to reach this glass-air interface. What's it going to do? What's your gut tell you? In physics, we like symmetry, right? So if we see that when you go from lower index to higher index, it bends towards the normal, we would like it probably to bend away from the normal, going the other way around. So I'm going to exaggerate this. It wouldn't, of course, be that much unless it was a really high index material. So you can see that if we consider other rays, what's happening? Let me use colored pen here. So I'm going to move this over here into greater than N1. Let's consider another ray that's incident upon this. And then now this angle is here. And that means it's going to bend away from the normal even more, you see? Like this. And so it seems that at some point we must be able to find some angle for which the reflected or the refracted ray bends at 90 degrees, which means that it never exits the material. And so we can take Snell's law and write it down. N1 sine theta I, which I'll call this N2 because remember we're starting in the high index material, equals N1 sine theta refraction. But I want to ask about the condition where the refracted angle is 90 degrees. So what I'm going to do is I'm going to let the refracted angle equal 90 degrees. And so what does that give me? That says that N2 sine theta I equals N1 times the sine of 90 degrees. And who can remember what the sine of 90 degrees is?
0.
Think about it. Right?
1.
Yes, 1. The cosine of 90 degrees is 0.
Yes.
That's because we think of triangle like this, right? And so we've got here's our angle, right? This is the adjacent part, or that we can get from the cosine, right? And this is the opposite part, which we can get from the sine. And so as this angle increases, the opposite part and the hypotenuse become exactly the same value, and we say that's equal to 1. The ratio of them is 1. Whereas the adjacent part becomes 0, because it vanishes as we increase that angle. So yeah, the sine of 90 degrees is 1, and so what we get is that n2 times the sine of theta. I'm going to call this now, instead of I, I'm going to call it C for critical. So this is typically called the critical angle, and this will be equal to n1, which means that the critical angle is equal to the ratio of the indices. And then, of course, you can solve for that angle by using the arc sine or inverse sine of n1 over n2. So let's just calculate a critical angle. Let's do 2, right? So let's do theta c in glass, maybe, and let's also do theta c in water. So this would be equal to the inverse sine, right? Remember, n1 is the medium, that's air. So really I could call that 1 over. So it's 1 over the index of glass, which is 1.52. I think it's 5.2. 1.52. And then for water, it's going to be the inverse sine of 1 over 1.33. So what are these equal to? And we'll take the inverse sine of 1 over 1.52. That is 41 degrees. So 41 degrees. And for water, it's going to be 1 over 1.33. 48, well, it rounds up to 49 degrees. 49 degrees. So what does that mean? All right, let's think about that for a second. Let's imagine that we're in a swimming pool, and we're lying at the bottom of the swimming pool. Now, don't go and do this in real life, you might drown. But if you were, let's say it's a really big swimming pool, and we're looking up, and we can see the sky. Let's assume that the water is nice and flat, right? The surface of the water has not been disturbed. And we'll see the sky. But if we look out at an angle, because this works backwards, right? This means that light coming in this angle, right, will arrive at this point. Light coming in at this angle will arrive at this point. So we can think of these rays going backwards. So the light that's coming in to the pool, stuff that's out beyond 49 degrees, all we're going to see is the bottom of the pool. So it'll be like sky, and then we'll see basically what will appear to us as a reflection of the bottom of the pool around us. And I'm sure you can go online and probably find an image on the internet that shows this effect. And maybe if you've done a lot of swimming in calm, placid lakes, you may have even observed it. So it's an interesting thing that light can get trapped inside the substance, so to speak. And that's totally internal reflection. So now we're going to consider lenses. And when we did our focusing mirrors, the spherical mirrors, last week, usually when you think of focusing of light in imaging, it's like you think of lenses, right? Lenses transmit light. So how do they work? Well, using this principle of least time, if we're going to arrive at some point, we need to consider optical paths. I guess I should have written this here, that have exactly the same. So if we start from here, we're looking for some way to make this happen. All right, so this marks a point in time, and so this ray, as it travels from here to here, this path will be the same length as these paths here. And so how do you do that? That's the question. If we introduce a material whose index of refraction is greater than, say, air, which we're assuming this is what our rays are in, then it will introduce a delay in the arrival time of these waves. So let me just, before I draw this, let me draw the following. I've got these three rays, and then I put a big, thick piece of glass in here. And this is coming in at normal incidence. And I'm going to use a term
let's call it a wave front, even though we haven't talked about waves. We'll call it the light front. So here we were at t equals 0, right? These three rays all depart at the same t equals 0. And then at some later time, t equals, well, just some later time t, we might find these two rays here, since they have basically traveled in the same direction in the same material, they're traveling at the same speed, so they'll travel the same distance. It's, the speed of light times this t will give us this distance here. But this ray didn't go as far, you see?
Yes.
And why didn't it go as far? Well, because it traveled through this material here, which we said was glass or something, which has some, N2, which is greater than 1. So its index is larger than 1, which means that this ray gets delayed in its arrival. So they're kind of separated.
Yes.
So we can imagine, right, using this principle of least time, finding a clever way to design a piece of glass to make these travel times, line up. If we were to do that, we would basically come up with the equation for a parabola, which you might remember from our discussion on spherical mirrors. It's easier to make a spherical mirror than a parabolic mirror. But a spherical mirror, as long as it's not too big, will be a good approximation to a parabolic mirror. And so we can create a couple of spheres like this. Let me just do my best job of drawing a couple of circles of the same radius. You get the idea. So its centers would be here. But if they're the same curve, if they have the same radius, then the average of these 2 points will be right here in the middle. And so what we call the center of the curvature of radius will now be in between these two. And so now what I'm going to do is construct this intersection here, like that. And then I'm going to get rid of the circles that I derived this all from, you see? And so what I now have is what we would call a, what do we call this? It's convex, so it would be a biconvex lens, I think, because there are two of them, right? It's two convex lenses back to back. If it was biconcave, it would look like this. But we'll talk about that's a divergent lens. This is a convergent lens, okay? We'll get into that in more detail later, but we'll talk about the convergence part now. So don't forget that we've got these two spherical surfaces here, right? And so this is going to somehow act like a focusing device. It'll have two focal points, one here, where this focal length distance is the same. So this distance would be F. I'm not going to draw because we're going to draw some rays here in a second. But this distance would be F, and this distance would also be F, little f, right? The point would be big F and maybe big F prime, okay? So you'll notice here it says thin lens. Why thin lens? So the assumption of a thin lens, right? The reason that we do that is, do you remember the lens equation from last week? Right? We got something like 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance.
Yes.
Well, if we let this be thin, meaning that the light doesn't travel through a lot of material, which means that we're basically going to neglect what goes on inside the glass. Well, so it's really thin, and so that effect is minimized, as opposed to a thick lens, which would have a lot of glass that it travels through. Then we can't ignore what happens inside. But we're going to ignore what happens inside, and we can do that as long as it's a thin lens, and that will allow us to use the same thin lens equation. I'm not going to rederive it because it would fall out exactly like it did before, except it won't be a reflected in. It's not a reflection that's going on. We're actually transmitting through it. So we'll use our rules, right? Remember we have C and then we have F. I'm going to come from this side. This will be my direction of incidence, okay? So, and there will be a primary axis, right? Which goes, I guess I should fix that point up a little bit. There we go. It passes like this, or you can call it an optical axis if you want. I keep using the term optic axis because I'm used to using that term in the work that I used to do. And optic axis really pertains to crystals that have, a particular axis, X, Y, or Z, which is, the where the dipole is aligned, for example. And so it's a kind of a technical term. But I think people sometimes call this the optical axis or the primary axis. Parallel rays, you remember, will pass through the focus. And so how would we map that out? We would draw a ray which is coming in parallel to the optical axis. And then what we're going to do is we're going to bend it through to the focus, like so. Notice how I kind of ignored the interaction here, right? But what's going on here, of course, is that there is refraction taking place on this curved surface. But I'm kind of ignoring the, say the second one, the second interaction when we come out, and also, the effect of being inside this glass where, my rays get closer and closer to the optical axis, will be inside the glass for longer periods of time because there's more of it. So I'm ignoring all of that, and I'm just kind of drawing the ray from this surface to this point like that. Then you have, rays that pass through the center, or the curvature the radius of curvature, this point C here, which is the average of this curvature going this way and this curvature going this way, which puts it dead center on the lens, will not bend, right? So light going through those points will not bend. If I were to start from the same point here, right? I guess I should draw my image. Yeah. Start from the same point, go through the center. So, and that's enough, right, to get an idea of where the image is. You'll notice it's inverted, but if I were to take a piece of paper and hold it right here, I would see an upside down version of whatever it is I'm imaging. But we can, one more ray we can draw, right? Remember that rays that go through the focus emerge parallel. I'm just trying to think, how am I going to draw that? All right. Stretching it just a little bit here, but that's all right. So if I go through the focus, then we come out parallel. So if we pass through the focus, then we will become parallel. And so those are the three rays that you can use to construct, where the image is going to form for a thin biconvex lens.
All right.
And I'm going to leave it to you guys as an exercise to try to figure out what the rays will look like from a what we call a biconcave lens, which would look like this. Again, it has to be really thin. This will turn out to be a divergent lens, whereas this is what we call a convergent lens. And if you're looking for an example of such a lens, any pair of what do they call these? I think magnifying glasses or reading glasses. They call them reading glasses. Reading glasses use spherical lenses. These lenses are spherical because they will focus light to a point. Remember that rays that come in from infinity and very, very far away will all be parallel. They will all pass through the focus. That's why if you take these outside and you see, I've got a light back here. You can see the light focusing on the whiteboard from the light back behind me here. Do you see that?
Yes.
Try it again. So it's somewhere around here. So it's it's about a meter, maybe half a meter. Might be a half a meter. These. Also, you can see an image forming of the light source there at the LEDs, and that looks getting blurry. Now it's pretty focused. Now it's getting blurry again. So somewhere around here, I'd say. All right, and then we're getting double image because there are two lenses. Right, I can block one of the lenses, and we'll just get one image. Okay, but if I take that outside, right, I can focus the sun down to a point, and I can start firing. You cannot do that with glasses like these because these are divergent lenses, and that's because that's how we'll talk about how we correct vision in a future lecture that will be coming up soon. So things to consider with this, right? I'm just telling you, this lens equation still applies, right? This focal length, this would be the object distance, this would be the image distance, okay, from here to here. Okay, this lens equation still works. You can think a little bit about, well, what happens if I move the object distance, or if I increase the object distance, right? If I move it farther back, what's going to happen to the focal plane?
Yes.
You can think about that, and I'll put some problems in your problem set that
deal with that kind of thing. And if you move closer, what's happening, right? If I move closer, what do you think is going to happen to this? Let's just think about that one real quick. If I get closer, what's going to happen to this image? Is it going to get bigger, smaller? Think about this ray going from the top of the arrow through the center of the lens, right? As this gets closer, what's that angle going to do? If I put the focus here, the object, say, here, right? Going through these 2 points here, we'll have, see that?
Yes.
So that's moving down. We would still have a parallel ray that needs to pass through the focus. So what do you start seeing when you get that? That's going to kind of extend out. So this ray will look essentially the same. You have to pass through the focus, and I'm kind of assuming that that's where the focus is. Well, I'll let you think about it nonetheless, okay? So give it some thought.
So lecture 23, we're going to talk about thin lenses and alternative equation. All right, so you remember the usual equation that we use, right, is that 1 over dO plus 1 over di, that's the distance to the image, is equal to 1 over the focal length of the lens. And here I'm writing the lens. I'm going to do it like this. This basically means that it would be a converging lens, right? And if I wrote it like this, we would be talking about a diverging lens. Just a little easier to draw. This is the plane of the lens right here. E is the center point of the lens. This point C I've labeled here, and this point G are the focal points of the lens. Over here, A is the head, and B is the tail of this thing I'm going to image. This is my object. It's got a height of h naught. That's the usual way that we write that. And then all I've done is I've drawn rays that come in parallel to the optical axis and pass through the focus, and drawn a ray that goes through the focus and comes out parallel after the lens. So those two rays I picked, I did not draw the one going through the center point, E. And we form an image, which is a real image, and it is inverted, of course, as all real images are. Which means if I held a piece of paper up here, I would see an upside-down image of whatever I illuminated over here, h naught. And this is the usual lens equation, which we derived in terms of spherical reflectors. But I told you it applies to this. There's one small change, though, and that's a sign convention. So if dO, the object distance, is measured here, will be a positive quantity. If it's a real image, then di, which is on the other side of the lens, will also be a positive quantity. And for converging lens, the focal length will be a positive quantity. If it was a diverging lens, we would call the focal length a negative quantity. So just a little bit of a convention. This is just to make certain things work out right. But as far as the ray optics go, you don't need to even worry about that. You can just do the geometry of it. But I want to point out a couple of similar triangles here. The first one is the triangle ABC, which you will notice is similar to triangle FEC. So whereas FEC, and you can see that this angle here is opposite this angle here, and so this being a straight line makes these two triangles similar. Now what does that mean for us? Well, that means that we can write that the height here in FEC, this height right here, this distance, is HI. So we can write that HI over F, that's this distance here, so this over this, is equal to HO over DO minus F. It's this little distance right here, right? So this is DO minus F. DO minus F. But that's not the only similar triangle I want to point out. We also have triangle IHG, 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 and triangle DEG, DEG. Again, these angles are the same because they are opposite angles. DEG, DEG. That means that H sub I over DI minus F, because it's this distance right here, right, from here to here, which is D sub I minus F, which is this distance, is equal to this distance, which is H naught, over F. Like before, let's solve this in terms of H sub I over HO, right? So that's the height of the image divided by the height of the object, right? And if I do that, I'm going to get F over D naught minus F, which will also be equal to D sub I minus F over F. And this gives us that F squared is equal to D sub I minus F times D sub O minus F. And so that's kind of a new version of the lens, an alternative version of the lens equation. It is the same as this if you rework this, but sometimes this can be more convenient. And so one place where it is in terms of the magnification that you get with a lens, which we can write now as H sub I over H of O. So we can pick either one of these. It's usually more convenient to pick this one, right? So the magnification will be equal to F over D sub O minus F. And there's one other adjustment that I need to make here. I need to add a negative sign here. And the reason I put the negative sign there is there's a sign convention that says that if the image is inverted and real, then the sign of it will be negative. And so we put this negative sign in here so that we have that convention. If it's a positive, if the magnification is positive, it will be virtual and non-inverted. And so in the next little lesson, we'll see an example of that. Any questions? This and this are just two forms of the same thing. Might leave it as an exercise to show that that's the case. Okay, it's just a little algebra. But this can sometimes prove to be useful.
Take that there. F squared equals
D sub I minus F times D sub O minus F.
is the same as 1 over DO plus 1 over DI equals 1F over F?
Yes. Okay.
Okay.
Yeah, okay.